Software engineering. Software engineering is the application of engineering principles to software development in a methodical and structured way. It encompasses a range of methodologies, practices, and tools to create software systems that meet specific user needs, are reliable, maintainable, and scalable. Software engineering is a field that applies systematic, disciplined, and quantifiable approaches to the development, operation, and maintenance of software. At its core, software engineering is about problem solving. Engineers begin by analyzing a problem, often working closely with users and stakeholders to understand what the software must achieve. From there, they design and implement solutions, using programming languages, frameworks, and tools to build the software. Testing is an integral part of the process, ensuring that the product works as intended and meets quality standards. Once deployed, software engineering doesn't stop. Ongoing maintenance, updates, and improvements are necessary to keep the software relevant and functional. Key aspects of software engineering. Requirements analysis involves gathering and defining the needs of users and translating these into specific, actionable requirements. In design and architecture, engineers create blueprints for the software's structure, considering factors like performance, scalability, and maintainability. Implementation is the actual coding phase where engineers write, review, and refine code to build the software's features. To ensure reliability, engineers test the software through various methods, from unit testing to user acceptance testing with real users. Finally, after deployment, the software needs regular updates, bug fixes, and adaptations to new technology environments. Requirements gathering and analysis. Requirements gathering and analysis stage aims to define the problem the software will solve, identifying specific needs and constraints. It ensures the project aligns with business goals and user expectations. In this stage, engineers collaborate with stakeholders, such as clients, users, and domain experts, to gather detailed information. Techniques like interviews, focus groups, and workshops help clarify functional, basically what the software does, and non-functional, which is performance or security, requirements. The outcome of this stage is a comprehensive requirements document, sometimes called a Software Requirements Specification, SRS. This document serves as a baseline for design and development and includes use cases, workflows, and detailed specifications. System design. Architectural design is a high-level design that outlines the system's structure and organizes it into components or modules, deciding how they interact. Architects often use design patterns, such as Model View Controller or MVC, microservices, or layered architectures, to address specific requirements like scalability and modularity. In the detailed design stage, each component's internal structure is specified, including classes, functions, data models, and algorithms. Diagrams like class diagrams, sequence diagrams, and data flow diagrams help visualize and document these relationships. The outcome of the design phase is a software design document or architectural blueprints that serve as guides for developers. Effective design minimizes potential issues during coding and maintenance. Implementation or coding. Engineers adhere to coding standards and best practices, such as writing clean, modular, and reusable code. Following standards improves readability, maintainability, and reduces the risk of bugs. Version control systems, VCS, like Git, allow developers to track code changes, collaborate, and manage different versions. This is crucial for managing updates, debugging, and allowing multiple team members to work on the same codebase simultaneously. Developers frequently integrate code changes into a shared repository, using automated testing and build systems to detect errors early. Tools like Jenkins and GitHub Actions are commonly used for this purpose. the code produced during implementation is ideally aligned with the initial design and requirements, building a functioning software product that meets specifications. Testing. Unit testing involves testing individual components or functions to ensure they perform as expected. Unit tests are typically automated and run frequently to catch issues early. Once components are individually verified, integration testing ensures they work together properly. This step identifies problems with data flow, API interactions, and interface compatibility. System testing evaluates the entire application to ensure it meets the defined requirements. It examines the software's behavior in an environment that mimics production. User acceptance testing, or UAT, involves the end users who validate that the software meets their needs in real-world conditions. This phase often leads to refinements or feature tweaks based on user feedback. A rigorously tested software product with identified and fixed defects. This stage ensures reliability, performance, and that the product meets quality standards. Deployment. Deployment planning is crucial to avoid disruptions. It includes scheduling the deployment, planning rollbacks in case of failures, and ensuring minimal downtime. Setting up the necessary environments, development, staging, production, and configuring servers, databases, networks, and security protocols for seamless operation. Many teams use automated deployment pipelines to ensure consistent and error-free deployments. Tools like Docker, Kubernetes, and CI/CD pipelines help manage infrastructure as code, streamline releases, and support scalability. For software involving user interaction, training may be provided to help users navigate new features, along with user manuals or quick start guides. The software is made available to users, running smoothly in the intended environment. For web applications, this might involve live updates. For desktop software, it might mean installation packages. Maintenance. Corrective maintenance is fixing bugs or issues that emerge after the software is deployed. This may involve releasing patches or updates to resolve functionality issues. Adaptive maintenance is updating the software to adapt to changes in the environment, such as OS upgrades, browser updates, or changes in third-party libraries and APIs. Perfective maintenance is enhancing the software to improve performance, usability, or add minor new features based on user feedback and evolving requirements. Anticipating and addressing potential future issues, which might involve code refactoring, improving documentation, or updating deprecated code libraries. Regular maintenance keeps the software relevant, efficient, and free from issues, extending its usability and ensuring ongoing alignment with user needs. Project management and methodologies. Agile methodology emphasizes iterative development, where work is divided into sprints or cycles. Feedback is collected at each stage, allowing for continuous improvement and adaptation to changing requirements. Waterfall is a linear approach where each phase must be completed before moving to the next. It is suitable for projects with well-defined requirements and little anticipated change. DevOps combines development and IT operations, emphasizing collaboration, automation, and continuous delivery. It focuses on quick, reliable updates and fast feedback cycles, enabling rapid delivery. Scrum involves structured sprints and roles to manage development tasks, while Kanban visualizes work in progress on boards for continuous flow. Effective project management ensures that software is developed efficiently, within budget, and on schedule. It also enhances team productivity, collaboration, and the ability to adapt to changes.